Hello everyone, I am Voicu Popescu and my co-authors are Elisha, Zirui, Zhang and Jorge Vazquez. We're all from Purdue University. The title of our paper is Complex Virtual Environments on All-in-One VR Headsets through Continuous from Segment Visibility Computation. So the motivation of our work is to try to overcome the rendering capability limitation of all-in-one VR headsets. This is unlikely to change anytime soon, even though we have desktop-grade GPUs that can render many triangles for very complex 3D data sets. It's unlikely that battery density will evolve sufficiently and that heat dissipation technology will evolve sufficiently and that such that headset GPUs have at par capability. So the typical solution for VR is to simplify the data set. So to the left would be a very complex and beautiful forest data set, and then what you typically do for virtual reality is you make it VR ready by resorting to some extreme simplification. As you can see, the tree canopies are replaced with blobs and so on. So we take the visibility computation approach for virtual environment complexity management. And just as a quick recap, the input is a 3D dataset model with triangles, call it T, and as well as a user region R, and then the output is to compute the subset of subset V of T that is visible from R. So find all the triangles that are in T and are visible from R. And if this visible set V is much smaller than the original data set T, then the complexity reduction is quite effective. Unfortunately, visibility is a problem despite decades of research. So here to the left, you see one approach, which is sample-based visibility. You see the user region R, and then a sample-based visibility algorithm will shoot these visibility arrays, will trace these visibility arrays to find visible triangles in a data set. Invariably, there will be some triangles missing. The other approach, fundamental approach to visibility, is to compute visibility continuously over the space of visibility arrays. So here the space of visibility arrays is partitioned into subsets, and then visibility is analyzed continuously on each one of the subsets. So our algorithm, our approach is to compute visibility along a camera segment and to do so continuously. So our goal is to find all the triangles that are visible at the pixel centers when a camera translates from a point A to point B. So to the left you have what an image looks like when the camera is at A. It's a single triangle and a single pixel is shown here, and that's the pixel center. And then as the camera translates to the left, that creates an apparent translation of the rectangle to the right, and the image at B shows the situation when the camera is at B, point B. Now here are the images shown together, if you want, in a coordinate system anchored to the camera. So essentially what happens is the triangle drifts from the original position to the right position. So the trail of this moving triangle covers all the pixels highlighted in green here, and they can be easily computed as a 2D convex hull of these extremal positions of the triangle vertices, the 6 triangle vertices, the initial and final positions. So what is important is to compute these visibility events, and a visibility event occurs when a triangle edge is exactly passing through the center of our pixel. So here is the first visibility event when the right edge of this triangle goes through the pixel, and then the second visibility event is when the second edge of the triangle is passes through the pixel center. So what one needs to do is to keep track at each pixel of the visibility events, which essentially define the subsets of the translation interval when a single triangle is visible. So in this example here, essentially the Z buffer is generalized from storing a single value to storing a list of depth intervals. So you see on the y-axis there is depth, the distance from the eye to the surface along that along the ray through the pixel center, and on the x-axis you have the translation, which is parameterized with parameter t here. So at first, from 0 to tk, no triangle covers the pixel center, so no triangle is visible. Then triangle 1 covers the pixel center, so it's triangle 1 that's visible. Then again, no triangle from TL to TI, from TI to TJ, triangle 2 is visible, which is closer than triangle 3, so triangle 3 becomes visible only from TJ and is visible until TM, and again, no triangle is visible from TM to 1. So here is a preview of all results. So you see here there is a virtual environment. It's a medieval city that has 2.3 million triangles, and that is pushing the limits of what can be rendered on an all-in-one headset. Now, if you compute the visible set corresponding to this rectangle along the main street, you see that the visible set has drastically fewer triangles, 10-fold fewer triangles, so only 0.2 million triangles, 200,000 triangles, as opposed to the original 3 million. And rendering frames out of the visible set produces frames that are of quality virtually at par, indistinguishable from ground truth. And ground truth, of course, is obtained by rendering the entire original data set, so the two frames are quite similar. The quantification of the error here, epsilon, is the percentage of incorrect pixels. So it's 0.02% pixels are incorrect, and the incorrect pixels are due to occasional triangles missing from the visible set. Here is a data set that has many more triangles, so the original virtual environment has 55 million triangles, and the visible set has only 4.2 million triangles, so again a 10-fold reduction with a small error, so the error here is 0.1%. Our algorithm also supports dynamic data sets, which with each vertex essentially in a virtual environment moving independently, and it also supports spherical particles, which prevents having to pay the cost of increasing the number of geometric primitives from the number of particles to the number of triangles through tessellation. So if you take every sphere and you tessellate it with 20 triangles, then you multiply by 20 the number of geometric primitives, the number of spheres, to obtain the number of triangles. So our algorithm works directly with these spherical particles. So this is an illustration of that. So these are bouncing spheres. They're all bouncing vertically on a horizontal plane, you see that the visible set has only 1,600 spheres as opposed to the 10,000 original spheres, and rendering frames from the visible set results in flawless frames in this case. So all visible spheres are found. So thank you so much. Here's an illustration of our work. So this video is recorded directly from the Meta Quest 3 on a Meta Quest 3 headset, and you can see it renders quite comfortably at 70 frames per second. And the quality is quite good. There are no visible missing triangles. And again, the user can walk anywhere on this main street or translate forward anywhere along this main street, as you can see right here. I apologize for for showing you a first-person video that has to be seen in a headset basically, and I'm showing it to you on screen, so it's a little bit disconcerting as the user is swinging their head to look around. So here's the other data set, another data set that we tested, the grass data set. So again, the frame rate is not 72 frames per second, but nonetheless it is quite comfortable, and we're demonstrating that we're porting these 55 million triangle data sets, or 45 million triangle data sets to a Quest 3 and render a very rich scene, this ground level view of the grass